Hello, Mr. Betts here. Even though this example looks fairly simple, I categorize it as a level 3 example because we are going to have to use some processes that are a little bit tricky to evaluate this. So first of all, this is an improper integral because if you look at the natural log graph, we know that the natural log approaches negative infinity or has a vertical asymptote at x equals 0. So the very first thing we're going to do is we're going to take care of that improper integral part by rewriting it as a limit. So I'll say the limit as, I don't know, a approaches 0 from the right side of the integral from a to 1 of the natural log of x dx. Now, the first challenge here that we've got to figure out is how to take the antiderivative of the natural log of x. Be careful when you're taking antiderivatives that you don't see something like this and just say, oh yeah, that's 1 over x. The antiderivative of natural log of x is not 1 over x, that's the derivative of the natural log. The antiderivative we actually evaluate using integration by parts. So to evaluate this, what we're going to do is we're going to say u equals 1, and we're going to, u equals the natural log of x, and dv is equal to 1 dx. So this is a little trick that we can do with integration by parts so that we can use a derivative of natural log, which we know, to evaluate the antiderivative of natural log. So du is equal to 1 over x dx, and v is equal to x. So this integral right here is going to be equal to u times v minus the integral of v du. So I'm going to rewrite this, and I'm going to be very careful with my work to make sure that my limits are still in there. Anywhere I have an integral and anywhere that I've evaluated an antiderivative, I'm going to put my limits on an evaluation bar. So we're going to have u times v, which is x times the natural log of x. That is not part of my integral anymore. I don't have to take the antiderivative, so I want to make sure that I'm evaluating that from a to 1 minus the integral from a to 1 of v du. So x times 1 over x is just 1 dx. Now I want to group all this together because that limit applies to the whole thing. All right, then we're going to have the limit as a approaches 0 from the right. I'm going to go ahead and plug in the 1 and the a for that expression. So we're going to have 1 times the natural log of 1 minus a times the natural log of a. And then with the other expression, the antiderivative there is just going to be x. So we're going to have minus x evaluated from a to 1. This is a pretty good example of why parentheses are important. I actually don't want parentheses here, but normally if we have an expression like this, we think that the evaluation bar applies to the whole thing. So by not putting the parentheses, that evaluation bar only applies to the x. So taking that to the next step, natural log of 1 is 0, so I'm going to leave that one out. I'm not going to start evaluating the rest of that yet. So minus, so we have plug 1 in for x and we get 1 minus plug a in for x and we get a. And plugging 0 in, the a part here is easy. So as a approaches 0, that's no problem at all. The challenging part here, in fact, I'm going to just get rid of that, so it's going to be minus 1. Challenging part here is going to be evaluating this expression here. So the problem with that is that as a approaches 0 from the right, we have 0 here times negative infinity here. And 0 times negative infinity is an indeterminate form. This is one case where we're going to have to use L'Hopital's rule, but to use L'Hopital's rule, we need 0 over 0 or we need infinity over infinity. So what I'm going to do is I'm going to make it one of those two by rewriting this expression. So before I do that, I need to condense my work a little bit because we've got more to do. So I'm going to take all of this and just squeeze it down a tad so that I have room for my L'Hopital's rule. So going on here, what I'm going to do is I'm going to rewrite that negative a over the natural log of a. I'm going to write it as, don't need that stuff anymore. I'm going to keep the natural log on top. So I'm going to say the negative natural log of a over 1 over a. So by doing that, what I've done is I've made it negative infinity over positive infinity. So we have that infinity over infinity form where L'Hopital's rule will work. So we're going to apply L'Hopital's rule. Technically, off to the side, we should write the limit as a approaches 0 from the right of negative natural log of a is going to be infinity. And the limit as a approaches 0 from the right of 1 over a is also infinity. So since we have infinity over infinity, we have an indeterminate form where L'Hopital's rule applies. So limit as a approaches 0 from the right of derivative of natural log of a is going to be 1 over a, so negative 1 over a. Derivative of 1 over a, that's a to the negative 1, is going to be negative 1 a to the negative 2. And that expression simplifies to just a. So if we multiply top and bottom by a squared, negative a squared, get rid of the negatives, we get just a. So this is the limit as a approaches 0 from the right of a minus 1, and 0 minus 1 is negative 1. So very simple looking integral, but we had to use an improper integral. We had to use integration by parts. We had to use L'Hopital's rule and put all of that together to determine that the area between the x-axis and the natural log function and the y-axis, this area right here, which is infinitely tall, is just negative 1. Has an area of 1, but it's below the x-axis, so it's negative 1.